welcome to the second week of the post-CCC ComSci Club. I forget what week that is from the beginning of the year, but that's not really important. Okay, so today we'll be going over the solution for one of the questions in the square root decomposition. And we'll be going over the idea of square root decomposition and its applications to one of the questions I posted in homework last week. I realized that the learning model that I decided to do, where I try to have you guys do the research and try to solve it, is probably not the smartest. So for this week we'll have a lesson, and then next week we'll have a lesson with problems. But in the meantime, the other square root decomposition problems, I've seen that not many people have attempted it. The other two problems are much harder, so I recommend you give those a try because they use the idea of square root decomposition, but in different ways. So you have to be able to adapt your code in different ways, and that's going to get you a lot of good practice for future contests. So let's look at the square root decomposition problem we chose, and that is DMPG 18S5, Mimi division. Okay, the question reads, for her birthday, Mimi is given an array of A of n integers. She then proceeds to form Q operations. 1 LRX, count how many numbers are in the subarray AL to AR, which are divisible by X. And operation 2, given U and V, is replace the youth number with V. Because you forgot to give Mimi a present, you decided to write a program to verify her answers. Okay, so the idea with this question is to break it up, hence the name of square root decomposition, break it up into blocks of size square root n, given that n is the size of the array. So if we take a look at this question, look at this example over here. If we had 16 numbers and there were 4, 5, 6, so on and so forth, you'd break them into blocks of size 4. So your first block would be 4, 5, 6, 8. Your second block is 3, 9, 5, 9. Your third block is 4, 16, 1, 15. And your fourth block is 5, 5, 6, 3. And we have our whiteboard over here. And we see the same array. And we see how there are 16 numbers. So n was 16. And then square root of n is 4. So we see that we have a 4x4 array, 2D array, technically. And we can perform operations from there. So the reason we use square root decomposition is because it has the idea of counting. And let's say I'm going with the first operation where I had to find how many numbers from this number over here to this number over here. Actually, maybe not another 6. Let's go to this number over here, are divisible by some number. And you have to check, it's all the numbers in between there. So it's starting from this red to this red. You go down like this, then here, and then there. And so if you try to do simple counting by storing all the factors and seeing if a number is divisible, that can work, but it's going to be slow. The idea of square root decomposition is that you have certain blocks here that are fully used. These are blocks, like what I mean by fully used is all the numbers 3, 9, 5, 9, and all the numbers 4, 16, 1, 15 are inside the query range. So instead of just counting individually, you can count the number of numbers that are divisible, the number of numbers in this entire block that are divisible by the number that you're trying to find how many numbers divisible by. So if it was x, you check, okay, out of this entire block, how many numbers are divisible by x? How many numbers are divisible by x? And then the remaining ones you do individually because you can't use the entire block. So you check if 8 is divisible by x, and then 6 is divisible by x, and then this is in the query range, so you don't need to do any more. And then down here you have to check this 5 is divisible by x. Now, why is this more efficient? It's efficient because in one block is at most root n. Well, we'll just say approximately root n, but it's going to be it's root n. But it's approximately root n, but we're going to say root n. And there's one root n elements. So if you were to check an entire block, you'd have a complexity of big O root n for just the query. And then so you'd have this bottom block, and worst case scenario is root n elements. But everything in between here, there's at most root n blocks. So if we went with the worst case scenario, which is going from the second element over here, and so actually no, that's not necessarily the worst case scenario. If we just went from the second element, and then we chose this element over here to be our range, then we have these two operations covered, and then you have to cover these three, and then these three. And so the time complexity of that is at most root n because of this, root n because of this, and root n because of this. And since this is the time complexity and they're all the same, the time complexity here is big O of root n. And so that's the idea of doing a range query, and seeing which numbers are divisible by x. Because what you can do is just simply add the total of each block. Now, that goes to say, with divisibility, since the thing with divisibility is that the numbers A1, AL, A2, blah, 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 to AN, and then are only less than 200,000. So we can store for each block how many numbers are divisible by x for all the x values. And then individually you can also do, is this number divisible by x or not? We can store that. And so that's going to be the idea of our code. Now let's just verify. We've considered one case where the values were in different blocks. We saw that with 5 and 6, and also this 6 here and this 5 over here. But if they're in the same block, like let's say we chose this 3 and this 5, then you only have to check within that one block. But the width of this block is at most root n. So in a sense, just by counting all numbers in the same block, you're only doing root n operations. So your time complexity, if they're in the same block, would still be root n. And if they were just one block off, you had 3 and 5. So let's just say we checked with this one over here. This one, actually, then you could use the entire block and check the count on there. So let's say we did 9 and 1. You just count all of these, which is going to be at approximately root n. And then you count these, which is approximately root n. And so you have 2 root n things to check. And so that's big complexity is big O root n. So, and that's just the idea of how there's no constant factor that you use in big O notation. And so that makes all possible cases of our range query be at worst case scenario big O root n. And now we have to look at replace the unit number with v. So with that, with that, you have to think of how can I make sure I delete all the factors that the previous number had, and then insert all the new factors that my next number has. And that's simply just going through and checking, hey, is this, remove all the factors. That's literally just checking all the entire list and saying, hey, I need to remove all these factors of the previous value. Let's say the previous value is x. I need to remove all these previous values, and then after bring the and then subtract it from your total block count of each factor, because we also need to subtract it from there. And then after you put the next number in, the new number. So the new number in this case is v. And so you put v in, and then you do the operation again, where you for every number that's divisible by v, you increase the counter of at that specific spot, if the number is divisible by it, yes. And then also the entire block count, you increase it by 1, because inside of that block you have one more new number that's divisible by, let's say, some number that you are testing at the moment. And so that's the idea of the square root decomposition. Now let's see how that comes into practice. So first what we have to do is get our code formatted in. So we are given an array A, and its max size is 200,000. So I just made max n and square root. Max n is the maximum size of the whole thing, but we're going to find it's irrelevant. And then square root, I just calculated the square root of 200,000 is 447, so I'm just going to go a bit above that and say 450. And now we can start our code. So int n and q, and then take in n and q. And then now we can find we can get our input and then put them immediately into our block orientation. We don't need to put it in a regular array because in the end we're just going to convert it anyways, and we're never going to use the array, so we don't need to. So let's go ahead and do that. So let's say we have, we should probably declare this outside. So int a, and the size is square root by square root. And then after we need our thing that's going to store all the divisible values. So it's called divs. So int divs, and the size is square root by square root. And now let's count. I mean, not count. So let's just get our input. So for int I equals 0, all the way, but not including n. So all the way, I is less than n and I plus plus. So I have an extra space here. Wait, what? Okay, maybe I had some problem with my thing. Whatever. Now I'm going to take in my array value. So int x, cn x. And then now I'm going to need to store it in the respective block. So I'm going to store as I divided by size, or not size, square root, and then I mod square root. And the reason I do this is because let's say we have all numbers in column 0. We're going from I equals 0, 1, 2, 3, blah, 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 and then you get to square root, value square root, in which case you're going to see that at square root, you have to go to the second column. So square root divided by square root is 1, and then mod square root is 0. So it'd be at the next column and then at spot 0. And that's how we're going to go from there. So let's see now. We can get our we can get int block equals I mod square root, and then spot equals I divisible divide by square root, and then spot is I mod square root. And now we can put in our value. So a at block at spot equals our number is x. And now we need to insert all the factors of x into the array. And so you have to recognize that, you can recognize that you can just go all the way from 1 to x and store it in, check all numbers and check if it's divisible by x. Or you can recognize that every factor is paired with another factor. And if you checked all the numbers up to including square root of x, then it's going to have its respective pair counted within it, because you're going to have that number and then x divided by the number are both factors of x. So that's what we're going to do because it saves time. So for int j equals 1, j is less than or equal to square root of x, j plus plus. And then now we can simply check if x mod j equals 0, checking if it's divisible. Then we can see that the divs in the in the block named block, so divs at block, and then the spot, did I do that right? No, not spot. Divs at block at j plus plus. Whoops. And then if the number j is divisible by x, then that means x over j has to be divisible by x as well, because that means that you're getting the number that's divisible by x, so it can be divided evenly into x. So x over j will be a value that's going to work. So divs at block at x over j plus plus. And the only case where this won't work is if j is equal to x over j, because that's saying if j was exactly the square root of x, no decimals, then they'd be counting twice. So that means we just have to check if j times j equals x, then we just say divs at block at j minus minus, because we're just undoing one of the operations. So at this point in this for loop, we're going to have for every block, you're going to have checked if for all the numbers from 1 to the highest number possible, which is x, it's going to be inputted whether or not how many numbers are divisible by x, not whether or not. How many numbers are divisible by x, and yeah, that'll be the counting for the block. So now we can go ahead and get our remaining input. And so, what is the order of the input? So we have taken a1, and we've automatically put in the square root decomposition, and then we have a query function. Not query function, just a set of queries. So we'll just go while q minus minus, so this will just go until we've completed all of our queries, because when q is 0, that means we've done q queries. And then now we need to take in our operation type. So int operation, and then cin operation. And there's two cases if operation equals 1, and then else, and this is the case where I'm just going to put else if, because why not, operation equals 2. You don't need to do this at all. Operation else if operation equals 2, because there's only one case, 1 and 2, but I don't know. I just felt like doing it. Okay, so now if we have operation 1, then we need L, R, and X. And keep in mind that this is 1 indexed over here, but our square root decomposition is 0 indexing. So, and that's seen with Li and Ri are greater than or equal to 1 and less than or equal to n. So when we take in our Li and Ri, then we're just going to subtract 1 from each of them. So it's Li, Ri, and our desired value is x. And so we'll just say cin Li, Ri, x, and then Li minus minus and Ri minus minus. So we're just getting rid of the 1 indexing. And then now we need to find the exact spot, the block for the L and the block for the R. And the reason we do that is so we can check if they're in different blocks, then anything in between, if there's blocks in between, then we can just add that to the total, because we don't need to actually do any counting. But if they're in the same block or they're one block apart, then we're going to have to do the full counting of the entire thing. But that's not a problem. Hopefully that's clear. So now we should say have our count variable here, int count equals 0, and get our blocks. So int L block is, and similar up here, it was the spot mod square root. So it'd be Li over, not mod, Li divided by square root, and then our block is Ri over square root. And so that's the blocks, and then we need the exact spot as well. So int L spot equals Li mod square root, and then the right spot is Ri mod square root. And so now we have all of our variables that we need, and then we can do some counting. So our first case is if L block and R block are the same. Let's probably write this down. If L block and R block are the same, we can just naively count. Okay, so what does that look like? That's just going to say if L block equals R block, then for every value in between, let's just go every index. For every index starting at L spot and ending at R spot, including R spot, and then getting every index in between, then we just check if A at, and then we just go A at block and then spot, similar to last time. So if A at L spot, and then no, this is not L spot. If A at L block and L spot, and I did not put my opening bracket here, mod our values x equals 0. So this is asking, is A of L block L spot equal x? Actually, I didn't realize. The blocks are the same, so we can use L block, but the spot is not necessarily the same. It's equal to I. I have to specify that. So if A of L block I mod x equals 0, then this number is divisible by x. So we just do count plus plus. And then that's the case if L block is equal to R block. And then otherwise, we need to check all of the possible values in the range from L block to the end of that, all the possible values inside of L block from the L spot to the end, and all the spots for starting from the beginning in R block, starting from the beginning to R spot, and then all the blocks in between, we can just add the total from the div 2D array at each block. So what does that look like? For int I equals L spot, I is less than or equal to I is less than or equal to actually no, I is less than or equal to square root I plus plus, and then there we just check if A at L block I mod x equals 0, and if so, count plus plus. And then we have to do a similar thing for int I equals 0, I is less than or equal to R spot I plus plus. And then here we just check all the things in the last block. If A at R block at I mod x equals 0, then count plus plus. And then now we can just do for every block in between from every block in between L block and R block. So and there may not be any because they might just be one apart, but we can just handle that case just by doing it in the for loop, in the sense of going from L block plus 1 and ending before R block. And if there's none in between, then the for loop just won't execute anything. So for int I equals, let's do this. For int block equals L block plus 1, block is less than R block, and then block plus plus. There's a lot of blocks here, sorry about that. I really hope I did this correctly. And then we do count plus or equals divs of block, so working with the current block, and then the number of numbers are divisible by x in that block. So divs at block at x. And then at this point, we'll have our total count value, whether it's L block equals R block or they're not equal. And then we can just print out our count. So that should work just fine. And now our operation 2. let's have a refresh. Replace the uth number with v. So let's take in our u and v values. So let's see, int u v, and then we'll take in the input for u and v, and then just like last time, u is a 1 index, just like li and ri were. So actually it's called ui. Maybe I'll change. Actually, no, never mind. Same idea though. It's 1 index, so we need to subtract 1. U minus minus. Simple as that. And then now we need to get the block and the spot again. So u block equals u over square root. And then actually I didn't specify int. And then u spot equals u mod square root. And so now we have the number at our spot. So now let's just store the old number. So now what we have to do is take the old number, apply the changes that we need, and then we should be good to replace the new number in. But instead of worrying about having the old number being taken away, let's just store the old number. So int old number equals, and right now before replacing it, it's stored as a at u block and u spot because that was a spot that it belonged to. And then we'll just immediately change it. So a at u block at u spot equals our new value was v. And now we need to remove all previous divisible numbers from the div count. And then so because we're moving the old number, and then now we need to add all new divisible numbers into the div count as we are entering the new number data. So what does that look like? Well, it's not too bad. It's going to be removing will be for int j. All right, we'll just do for int I equals 1. I is less than or equal to the square root of the old number. We're just going to do the same idea as last time, or the same idea as up here really, except that we're just doing minus minus instead of plus plus. Square root of old number, I plus plus, and then we're checking if I mod, actually no, if old number mod I equals 0, and then if so, we need to subtract the, remove the factor of, and we're still in the u block, and we need to remove the factor of I from the total count in u block, and then we need to remove the factor of old number over I. And same idea as last time, there's one case where this doesn't work, and that's when I is equal to old number over I, or I squared equals old number, and that's because you're subtracting twice. And so to counteract that, we just go if I times I equals, let's put some space in between. If I times I equals old number, then divs at u block at I, supposed to see index like this, plus plus, and that should look good. And then now we need to just do the exact opposite where we add all the data. So we'll just copy the code here. Square root of the new number is v, and so we just replace this with v, and then we're entering new data and we're adding it, so plus plus. Oh, I just realized I never put minus minus over here. And then here we need a plus plus, and then this is v, and this is v, and then this is a minus minus. So let's read that one more time. So we're looping from 1 to square root of v, and we're checking if v is divisible by I, and if so, we're increasing the count of divisibility by I in the U block, and then V over I will also be divisible, and then I times I equals V, and then div at U block at I minus minus. And that should be good, and we don't need to output anything in that case. So let's test if this works. Let's copy this sample. Whoa, crashed. Okay. Let's check it and see if it works. If we copy paste it, we have 5, 2, 1, 2, and that matches our sample output. And if we want to see that more combined together, because that wasn't necessarily the best combination, it was hard to read. 5, 2, 1, 2. We got our sample output. Hopefully this works, but we'll find out in a few seconds because I'm going to submit this code. And let's see it. Wow, okay. That failed really fast. We have a bunch of zeros. Okay, give me 1 second. It was just a simple issue. The size of divs is not supposed to be for every number. It's supposed to be for every block, and then you're supposed to check all numbers. So this is actually supposed to be max n. So now this should work. And let's check it out. Pretty simple problem, but would have been hard to find if I didn't look carefully. Yeah, let's see it. Okay, so it looks like it's working. As you can see, it's taking a good amount of memory, and that's natural because it's you're essentially taking square root of 200,000 by square root of 200,000, so that's 200,000 things to store, and then you're doing that at 200,000 by square root of 200,000, so that's a lot of things to store. So naturally, it'll take a lot of memory. And we see that it works. And it worked pretty well. And our time limit, what was our time limit? Our time limit was 2.5 seconds. And then worst case scenario, we passed with 1.803 seconds. So not too bad. But yeah, this is the idea of square root decomposition. It's using the fact that you can sum up the total of blocks. And then the worst case scenario of blocks allows it to have the same time complexity as if you counted each thing alone within one block. So it's a clever trick that you might find sometimes. It appeared on CCC 17S5, except slightly different in the sense of you had to do a lot more optimization. But that is one of the problems that I've assigned for homework last week. So yeah, this is the idea of square root decomposition. And yeah, let me know if you have any questions. This is going to be all for this week. Relatively short lesson, but I don't plan on making lessons very long these days because I don't want you guys to get bored, obviously. And yeah, so that's all for this week. And yeah, we'll see you guys later. Take care.